Hey everybody. So we are going to look at some more integrals. We're building up our toolbox of kinds of integrals we can handle, and as you might have guessed from the title, we're going to be looking at some trig integrals. And there's going to be several of these videos on this topic, so I'm just going to, we're going to kind of break them up into categories. And one of the categories is going to use what I have written here, sine squared x plus cosine squared x is equal to 1. This is a really fundamental trig identity that you should know. This one is very, very useful. It shows up all the time. Let's see how we can use it. We've actually seen a couple of these in some videos back, but we're going to kind of see the full use of how we can use this identity to get ourselves out of some integrals that are otherwise very difficult. So I'm going to do several examples, and we're going to summarize what we've done in a rule. The rule is quite a mouthful. It has all these different cases. If we're in this case, do this thing. In this case, do this thing. But I think from the example, I hope you'll see that it's a little bit intuitive once you see what's going on. They're all kind of the same idea, and with a little bit of trial and error, it's quick to see what sort of strategy you should use. So let's take a look at the following integral. Suppose we want to find an antiderivative for sine cube x dx, okay? So what we're going to use is this identity here, except we're going to use it a little bit differently than it's written here. I'm going to subtract this cosine squared to the other side to get this, okay? And this is what's going to prove useful to us, because our first step is going to be to rewrite this integral as sine squared x times sine of x dx, okay? Maybe this is a good time to remind ourselves that sine to the n of x just means sine of x to the nth power, okay? So I've got 3 factors of sine sitting here, and I peel 1 away, okay? Another side note, there's one of the most horrible abuses of notation, because we usually mean sine to the n of x equals this, unless we write this, in which case we mean arc sine of x, which is not sine to the -1 power. I know it's terrible, but it is, these are both used, and we just have to get used to, from context, knowing which one we're talking about. Okay, anyways, back to the problem at hand. Sine cube x dx is equal to sine squared x times sine of x dx, the antiderivative of both of those. Okay, so now we're going to use this identity as I've written over here, and replace sine squared with 1 minus cosine squared of x times sine of x dx, right? And now what we have is a nice situation, because you might notice that if I let u equal cosine of x, right, then du will equal negative sine of x dx. And so this integral becomes 1 minus cosine squared is just 1 minus u squared. Sine x dx becomes negative du. So I'll put the negative out front. And we end up with negative, and then the antiderivative of what I have here is going to be u minus 1/3 u cubed plus some constant. And then we'll put our substitution back. U was cosine of x minus 1/3 cosine cubed x plus c, okay? And there it is. We might want to clean this up a little bit, distributing that negative. I get 1/3 cosine cubed x minus cosine of x plus c, okay? And that either way was fine to write it. I just happen to like it, how it looks this way. Right, and so at the end of this, all what we have is that the antiderivative of sine cubed x dx is what we have written here on the right. Now, let's go ahead and check it. Let's take a derivative. This is always a good way, especially when we're using a new method, to make sure there's nothing faulty in our method, or I guess identify if there is. This doesn't guarantee anything. It is a universal method, but it would certainly tell us if it didn't work. So taking this derivative, first I have a chain rule, so the 3 comes down, hitting the 1/3 makes 1, so I'm left with cosine squared x. Then I have the derivative of cosine, which is negative sine x, plus negative cosine's derivative is negative sine, but sorry, cosine's derivative of negative sine, I've got a negative there, so I have plus sine of x, okay? Which does not look like what we started with, right? The derivative of this was supposed to be sine cubed. However, if we factor out a sine of x from these two terms, the sine x term has a 1. The cosine squared x term, all that's left from this sign is the negative, so we get a minus cosine squared x. If we look back at the identity, 1 minus cosine squared x is just sine squared x. And then sine x times sine squared x is sine cubed x. So this indeed is an antiderivative. Okay? And this is actually going to be a common occurrence where we take a derivative to check our answer and we don't get exactly what we had when we started, but we, through the use of some trig identities, can discover that actually it is the same thing. Okay. So let's complicate things. Okay, let's try the following. This one's a bit uglier. Okay, but actually I'm going to go back really quick. I just want to point out this thing that we did here, where we peeled off one of the factors of sine, leaving a sine squared, is going to be a common thing that we do here, right? The reason being, this sine squared x equals 1 minus cosine squared x. We could also rearrange this to get cosine squared x equals 1 minus sine squared x, right? And so in both cases, we're looking for sine squared or cosine squared in our integral to make this substitution. And so as we move forward, as we make these more complicated, though, we'll still see the same idea show up again and again. So let's see, let's look at sine squared x times cosine to the 5th x dx. Okay? So this is a decidedly more difficult integral. There are a few things that might make sense to try. We do see this sine squared here, and we might be wondering, should we try to take 1 minus cosine squared and substitute it for sine? You try that. However, what you end up with is a whole bunch of cosine, powers of cosine, which we don't have a great way to integrate typically. Instead, we're going to try something else, right? And this is something you would just discover through trial and error. And so we have humans in the past have figured this out for us. And so we're going to use their good work. I'm going to rewrite cosine to the 5th as, well, let's do this a step at a time. We're going to do several things to it. The first thing I'm going to do is change cosine to the 5th to cosine to the 4th times cosine of x. Again, peeling off that factor of cosine. Then I'm going to take that cosine to the 4th and do the following. Write it as cosine squared squared cosine of x dx. All right, I have a thing squared, square it again, you get to the 4th power. So all I've done is change the way that I write it. Now, this cosine squared in here, remember that identity from before, cosine squared x is equal to 1 minus sine squared x when we rearrange it. I'm going to use that identity here. Sine squared x, 1 minus sine squared x. Oops. Let's be consistent. cosine x dx. Right, so I've taken that cosine squared and made it into a 1 minus sine squared. Now, we're going to use a substitution again. In this case, we're going to substitute u is equal to sine of x, du will be equal to cosine of x dx. And notice, all we have up here is sines of x. Anyways, we have several instances of sine of x, and then we have a cosine x dx factor, and so we can account for everything. Sine squared becomes u squared. 1 minus sine squared becomes 1 minus u squared, squared. Cosine of x dx becomes du. Okay. And now we have a very solvable integral. The first thing I might do is expand this, what's in the parentheses, I get u to the 4th minus 2u squared plus 1. Then distribute that u squared, so I have u to the 6th minus 2u to the 4th plus u squared. And now this is a pretty simple application of the power rule and our properties of integrals that let us break it up over these additions and subtractions. So each antiderivative here, let's see, we have u to the 7th over 7 minus, we'll have 2u to the 5th over 5 plus u squared over, u cubed over 3 plus c. And then we just come back with our substitution. The antiderivative, let's see, what was our original? Sine squared x cosine to the 5th x dx. Looks like it's 1/7 sine to the 7th of x minus 2/5 sine to the 5th of x plus 1/3 sine cubed of x plus c. Okay, right. This is not an obvious antiderivative when we start. I'm going to leave checking it up to you. Okay, so you take a derivative of this, they've each got a chain rule. You'll definitely have to do some algebra, combining like terms, using some of these, excuse me, using some of these identities to get it to look like how it started, but this is indeed the antiderivative. Okay, now let's do one more example. Actually, let's stop and look at these. Notice in both cases, when we peeled off the sine from sine cubed, we were left with a sine x dx and a sine squared, right? And we kind of thought about the sine squared first, yet letting us use this identity of sine squared x equals 1 minus cosine squared x. So we wanted to use this thing here, so we created this piece here to write this. But it did something else at the same time. It gave us this sine x dx, which was very useful for our substitution. A very similar thing happened here. Right? We found cosine squared so that we could use the 1 minus sine squared, but at the same time, we peeled off one factor of cosine, leaving a cosine x dx, which gave us exactly what we needed for our substitution. Okay, so this gives us our first set of rules for doing these trig integrals. Okay, so here's the rule. I'm going to call this the strategy for integrals of the form. So we're looking at antiderivatives where we have sine to the nth power of x, cosine to the nth power of x dx. In other words, we have sine and cosine to various powers. Okay, what do we do in these situations? Here we're saying m and n are positive integers. Okay, So if n is odd, so if the power on cosine is odd, we'll use cosine squared equals 1 minus sine squared x. Okay, right? This is the case that we did in our second example. Cosine was to the 5th power, and we ended up using cosine squared equals 1 minus sine squared x, right? So if n is odd, if the power on cosine is odd, we're going to use this identity. And the way we'll use it is we will write, so let's see, we'll need a little space here, sine to the mth power of x, cosine to the nth power of x dx. We can rewrite this. So if n is odd, that means n is equal to some integer times 2 plus 1, right? Every odd number is an integer times 2 plus 1, right? 5 is 2 times 2 plus 1. 13 is 6 times 2 plus 1. What that means is I can write this as cosine to the 2k power times cosine of x dx, right? So if n is an odd integer, I can think of it as 2k plus 1. Like when we had to the 5th power, we thought of it as 2 times 2 plus 1. So we had a cosine to the power of 4 and a cosine to the power of 1. And then we rewrite this cosine to the 2k power as cosine squared x to the kth power cosine of x dx, right? Again, all I'm using here is what an odd number is, and then rules of exponents, and then we can use the u substitution. Oops, sorry, I skipped one step, pardon me. We'll rewrite one more thing. We can now write this as sine to the mth power 1 minus sine squared x to the k power cosine of x dx. And then we'll use u equals sine of x, which means du equals cosine of x dx. Okay? It's a mouthful, but it's what we did in this second example, right? I peeled off a factor of cosine. I rewrote because remember, cosine started odd here. So when I peeled off one factor, what was left was an even power of cosine, this cosine to the 4th. I rewrote it as a power of cosine squared. So because it's even, I can do that, right? Cosine started as odd, peel off 1, it's now even, which means I can write it as cosine squared to some power. And then use our substitution, our trig identity substitution, that even power, that cosine squared becomes 1 minus sine squared, and then use a substitution. When you do this, everything you have here is now powers of u. You do some expanding and some algebra, and then you can just do a very basic integral and redo your substitution at the end, or undo your substitution at the end. If m is odd, we're going to use sine squared x is equal to 1 minus cosine squared x, right? Again, this means that m is equal to some odd number, which means it's an integer times 2 and then add 1. And we'll do the same thing, just reversing the roles of cosine and sine. So again, I'm going to take, I keep writing sim instead of sine because that m is coming next. Sine to the mth power. What we're left with is sine to the 2k power cosine n of x sine of x dx. I stripped off, peeled off that one power of sine because it was odd, leaving me with an even power of sine, which I can write thusly. sine squared to the whatever, to the k power. And I have cosine to the n power x sine x dx. And then I use the substitution. In place of sine squared, I write 1 minus cosine squared x to the k power, cosine to the n power x sine x dx. And now my substitution is u equals cosine of x du equals negative sine x dx. And we have exactly what we need. We'll have powers of u when we're done. The du takes care of that extra sine x that's left behind. Okay, so again, that one's very much like the first example, although in that example, I only had powers of sine, but the same strategy applies. Okay. If they are both odd, use either. It won't matter. You can use either one you want, either method. If they're both odd, it's up to you which one you decide you want to use. Okay, sorry about that. If there was a little gap, I had a little technical difficulty. So carrying on now. So we just looked at, we're looking at these integrals of the form s to the m of x cosine to the n of x, where that's our integrand. And we just came up with some rules to do if one of them is odd or if both of them are odd. However, what happens when they are even? So let me just state the rule, and then I will give you an example of using it. If both are even, we have several other trig identities that we can use. So let's see, we'll have sine squared x is going to be 1/2 1 minus cosine of 2x, or cosine squared x is 1/2 1 plus cosine of 2x. And then another identity that might prove useful, sine of x times cosine of x is equal to 1/2 sine 2x. Okay, so these can prove useful when they are both even. Let's do an example of one such situation where we might use it. So let's just take a simple one, the antiderivative of the cosine of x squared dx. Okay, whoops, sorry, I just hit something funny. Oh, I had it the size off. All right, this is a little better. It's a bit big, but that's all right. So all we're going to do is use this identity that I just gave us and replace cosine squared with dx, right? The problem is we don't have an extra cosine sitting around to peel off, leaving behind a cosine squared. And so we're going to use this identity instead. Okay? And this now becomes an antiderivative we can take. So I'm using some rules of integrals here, splitting this up into two antiderivatives, pulling that 1/2 up front. The antiderivative of 1 is just x. The antiderivative of cosine of x, a cosine of 2x, is 1/2 sine of 2x. You can use a u substitution if you want to see that there. This is an easy enough derivative to take to see that this works out, plus c. Right? And that's it for us, right? This is, I'm just doing one simple example for now to give to show you these other identities, right? But with these identities in hand, this gives us a whole new class of integrals that we can now handle that were not were not there for us previously. Okay, so there's some more to come, but I'll do that in another video. That's it for this one. Thanks, everybody. See you next time.